is higher in denser clouds. So how massive are those clouds? How large are those clouds? And how wouldn't it be unthinkable that the IMF is completely different in those, I guess, small, not very massive clouds?
We don't know, and yes.
Nice, concise answers.
Yeah. The picture is they're like 10 to the 4 to 10 to the 5 solar masses, right? That's what I assumed here. The sizes are like tens of parsecs, right? So very similar to the things we see in like the lensed objects. And indeed, the IMF may very well be different at these densities. So that's definitely an open.
Okay, let's thank Rachel again. Do you have the microphone?
Yep.
I will warn you when you've got 5 minutes to go.
Looks like my movies will be sluggish. Yeah, okay. Anyway. Or should I connect with HDMI? Okay, just imagine that they're like super impressive. And can I? Oh, okay. If it's possible. Oh, wait. But do you need to connect it? Or? Yeah. Anyway, let's do sluggish mode. All right. Yeah. Anyway, should I start? Okay. Yeah. First of all, I would like to thank the organizers. I'm sure everyone will agree, but it's always a lot of fun to be here in Santa Cruz. And in this talk, I'll start making a transition to tomorrow's sessions. I'll be talking about formation of galactic disks in very early universe and how essentially disks emerge from this very early, bursty, chaotic galaxy formation at early times. And so as we have seen, this early burstiness is a very appealing scenario for explaining this overabundance of very bright galaxies at early times. And the puzzle, the question is how to reconcile this early burstiness with the also large population of early galactic disks, as was also revealed by JWST and earlier by ALMA. And although all these puzzles are coming from high redshifts, the original motivation for this work came from much closer to home, from the galactic archaeology. It's already there, but it's very sluggish. Now I regret making all the transitions in the slides. So yeah, the original motivation came from local galactic archaeology, where thanks to surveys like Gaia, we can now see the imprint of this early evolution in the structure of the Milky Way itself and the formation history of the Milky Way disk, as have been shown in multiple works over the past few years, and this can be done differently. And here, for example, in this plot made by a student at Harvard, Vedant Chandra, we can look at the properties of populations of stars, such as, in this case, orbital circularity, properties of orbits, orbital circularity, as a function of stellar metallicity, which can be, with some caveats, thought as a proxy for the formation time. And we see this population of stars at low metallicities that are arranged in this kinematically hot component located in the center of the galaxy, that is thought to be a remnant of this very early evolution before Milky Way had the disk. And in the same data, we can see this sharp transition that formation or spin up of the galactic disk and with the high metallicity stars arranged in this disky configuration. In the first paper where population was first discovered, Vasily Belokurov and Raykovtsov, they also compared this spin-up feature with predictions of high-resolution galaxy simulations. And here it's shown in terms of the rotational velocity of stars. So it's the same idea that we can see in the Milky Way, this sharp increase in velocity at roughly 10% solar metallicity. And in simulations, we see a similar feature, but it appears at significantly high metallicity, implying that in simulations, formation of galactic disk is delayed. So one of the ideas that came out of this results is that maybe this high burstiness at early times that is revealed in the simulations, and it helps to explain this early UV bright galaxies, maybe this is also something that prevents disks from forming early. On the other hand, it can be that the Milky Way is just an unusual galaxy and it forms unusually early. And in fact, when we look at larger samples of Milky Way like galaxies, as we did here with the TNG50, we see that there is a substantial, sizable population of Milky Way mass galaxies that form disks as early as the Milky Way. It's roughly 10% of the Milky Way mass galaxies in TNG simulation. So this makes it a bit inconclusive because on the one hand, the way how star formation and feedback modeled in large simulations like large cosmological simulations like TNG50, they produce very smooth star formation histories which are significantly less damaging for galactic disks than what's done in high resolution simulations. So it's not clear from this whether it's this early formation of the Milky Way just a feature of the assembly history of the Milky Way, or is there an intrinsic trade-off between this early burstiness and formation of the disk. So to address this, what we did, we took one of these early forming Milky Way-like galaxies from TNG and simulated it with more detailed physics of explicit formation of cold ISM and ISM turbulence and star formation feedback coupled with the dynamical state of the ISM. And movies look nice and all, but in reality they're even more impressive. So here is just a comparison of the original model, TNG, and this new simulations run with ART code, so I'll be calling them ART. The key difference is this, as I said, is the explicit formation of this cold turbulent interstellar medium. And you can see these drastic differences at small scales, the formation of these dense structures, which result in the end in the drastic differences in the star formation histories. So in terms of the star formation rates, the star formation history becomes significantly more efficient, which consistent with what has been discussed already at earlier talks. And it's significantly more bursty than in TNG. So this early efficiency results in the simulation in this new this new simulation reaches a significant mass early on, such that it becomes massive enough to sustain stable disk significantly earlier. Forms in the simulation at redshift around 6. And again, here I'm reminding you that this particular object is not a typical Milky Way mass galaxy from TNG. It's a galaxy that forms disk very early. But in TNG model, this happens at redshift 3, while with this new, more detailed model, this happens significantly earlier at redshift 6. So here we have essentially both very early formation of the disk, at the same time, very bursty star formation history. So it shows that there is no intrinsic contradiction between the two. And the key ingredient that helps to reconcile these two effects is the way how star formation feedback are coupled to the turbulent dynamics of the interstellar medium. So here in this simulation, one of the important features is that we use this so-called large eddy simulation methodology to predict the turbulent state of gas on unresolved scale. So essentially, it's the way how turbulent flows are modeled in industrial applications. And in this simulation, it helps us to predict the velocity dispersion in each resolution element on each time step. So then what we can do, we can couple this information about small-scale turbulence with models of star formation in turbulent medium and predict the variations of this so-called star formation efficiency per freefall time instead of assuming a fixed value as is often done in the simulation. So as a result, we get this dynamic variation of star formation efficiency both in space and time, which in this projector you can kind of see it, right? So there's a significant variation of star formation efficiency per freefall time. However, if we look at the average values, so here it's shown here in the bottom, what's interesting is that even though the model itself is ignorant of the star formation in galaxies, so the value of efficiency predicted by the model can be anything between 0 and 1, when we apply it at this high redshift regime, we get the values which are close to 1%. So typical for, they're similar to what we observe in the local universe. But on top of this, what's important is this huge variations of the star formation efficiency per freefall time, which in fact dominate the short-term variability of the star formation rate in this model. So if we account for these variations, the global total variations of the star formation rate becomes such that they can explain the variations needed to explain this high redshift UV bright galaxies seen by JWST. And at the same time, the nature of these variations is such that it enables this early disk that forms at redshift 6 to survive. So there are two factors why disk survives in this case. So first factor is that this variability, this burstiness is qualitatively different from what people usually talk about when they talk about burstiness in galaxies, burstiness star formation in galaxy simulation. Because star formation rate in the galaxy and that the local star formation efficiency per freefall time is fixed, then okay, great. If we assume that the star formation efficiency is fixed, then the only way to change star formation rate is by changing the total amount of star forming gas, so its densities, right? So we need to significantly perturb the gas reservoir, so essentially we need to explode the galaxy. While if we allow local variation of star formation efficiency per freefall time, we can keep the gas reservoir intact and change the star formation rate globally by changing the global turbulent state of the galaxy, which is much less damaging for the disk. So this is the first factor. And the second factor is that at exactly the moment when the disk forms, the fluctuations of the star formation efficiency also change dramatically. They decrease substantially. And the reason here is that the mode of turbulence driving that creates these variations also changes. So before the disk formation, it's driving of turbulence by process like inflow of material from the halo scale, in mergers of galaxies. So essentially, it's processes that operate on large scales. And the visual analogy here that I have is that it's this vigorous turbulence that you can observe at the bottom of the waterfall. While after the disk settles, it's a much more mild process that operate inside the disk, such as the development of disk instabilities and effects of feedback, which operate on significantly smaller scales. So there's a second factor that this qualitative change in the mode of driving and the mode of these fluctuations, it's another thing that helps this early disk to survive. And in the end, I'll just flash quickly some other results, which I'll not go into details, just in interest of time, and I'll give some extra time for questions. And the idea is that these different modes of turbulence driving, they also imprint fluctuations on different time scales, which can help to make some testable predictions for distinguishing between these regimes observationally, as can be quantified in this so-called scalograms, which are so essentially it's very similar to Fourier transform, but in the way that it also preserves time information. So essentially, you can see the spectrum of the fluctuations as a function of time. And before the disk formation, and this global variations imprint fluctuations on significantly longer time scale, and with a larger magnitude than at later times, where it's more like white noise. And then as a result, it also imprints in the difference in the star formation variability on different time scales. So by comparing the star formation rates, variability averaged on different time scales, we can distinguish between these two regimes. So if you want to know more details, please ask me later. And with this, I'll just leave my conclusions. Thank you.
Thank you very much. Okay, where do we start? Let's start with Sandy.
This process is taking place at high redshift in your simulation. Are there local galaxies that are still sort of early in their dynamical evolutionary history where this transition might be taking place? In other words, could you recommend looking for low redshift analogs of the bursting state?
Oh, it's interesting. I mean, it's hard to, yeah, apart from actually being in the process of formation, it's also, yeah, as we talked, it's significant.
What's the criterion for transition? And is it universal at all times?
Yeah, that's an interesting question. So I don't think there are direct analogs, in part because the universe was much denser. So
What's the criterion? Right?
what formula? I'll need to think about it. Yeah, in this case, so there is simply it's the galaxy. So this transition appears to happen at when galaxy becomes massive enough. So okay, that's one of the criteria will be the shape of the potential. We can talk about this. Yeah. Okay.
Quick question. So on Wednesday, I'll talk a little bit more about low redshift things like this, but this is fantastic. The one thing I was really interested in is it looks like your sort of spin up is almost instantaneous.
Yes.
Where it's like at Z of 0 in the Milky Way, there's this sort of thick disk phase, which is sort of characteristic of the spin up. This
Yes.
seems to happen very quickly. I think it's like it snaps to epsilon of 1 like almost instantaneously.
Yes.
A little shocking. So what's happening there? Do you think this is rare? Do you think this is typical?
No, that's actually, yeah, that's what we see. So essentially here you can see, so this is also, yeah, I went very quickly through this, but this is also orbital circularity, but it's at birth.
Yeah.
So essentially, if you look at the instantaneous population, then you see the formation of the Milky Way, of the disk on the local dynamical time. So
Yeah.
essentially it tells you that the process that triggers formation is local, right?
Yeah. In the fire simulations, it's not like that. There's a spin-up phase that lasts quite a while. So it's interesting you see it very differently here.
Yeah. But then another thing is then when we compare to the archaeological data,
then you get some heating.
we can talk about this.
Okay, I think we need to go on. so more pause. Okay, Harley. Oh, so you need to trade microphones, and you need to share your screen there.